A very good morning to all. Welcome to the fourth day of the online short-term course. I'm so happy to have this chance to introduce you to our today's speaker, Dr. Suparna Saha, Associate Professor, Department of Computer Science and Engineering, IIT Patna. Dr. Saha has received MTech Gold Medal and PhD degree in Computer Science from Indian Statistical Institute, Kolkata in 2005 and 2011 respectively. She had worked in the field of deep learning, natural language processing, and machine learning, bioinformatics, and multi-objective optimization over the past 10 years. Aside from the talents and the advocacies, Dr. Saha is also a prestigious author, co-author of over 250 papers. She is the recipient of the Google Indian Women in Engineering Award 2008, SERB Women in Excellence Award 2018, and SERB Early Career Research Award 2018, and many more. She has worked as visiting professor in renowned universities in countries like France, USA, Japan, and Germany. Recently, her name has been included in the list of 8 leading women scientists in the area of AI in India, published by India AI. And also, she is an editorial board member of IEEE Internet Computing. Today, Dr. Saha is here with us to give an insight on the topic unsupervised classification techniques. So I request you all to please join me in welcoming Dr. Sripanna Saha.
Thank you.
I
Thanks a
do.
lot, Dr. Ankit. Am I audible?
Yes, ma'am.
Yeah. Thanks a lot for the nice introduction and thanks for inviting me in this workshop. So, can I share my screen?
Yes, ma'am.
Yeah, is it visible?
Yes.
You can see my PPT now, presentation on unsupervised classification techniques.
No, ma'am, it's not visible.
It's
not
visible now. It's visible now.
Okay, so it's visible.
Now it is not visible.
Oh, what is happening? Because I can see.
Ma'am, you can just try it once more time. You
Okay.
can share it one more time. Yes.
Okay.
Visible, ma'am.
No, it was coming and then.
Yeah, ma'am, yeah.
So you can see, na?
Yes, ma'am.
Yes, ma'am.
Okay. So I am now doing full screen. Is it visible now, full screen? Or it is small, still small?
It has gone, ma'am.
It's full screen?
No, ma'am.
No, ma'am.
Because I am sharing, I don't know what is happening. Okay, so the screen is visible, na? The PPT is visible, not the full screen.
Yes, ma'am.
Okay. So I think I should go ahead.
Ma'am, now it is not visible. Ma'am, you can share your PPT with us. If you want, we can load it from here and then you can take control.
Okay, acha. How in that where to share the same mail ID?
Yes, ma'am. I will ask Abhinav sir to share mail you, and you can mail your PPT on his email ID. He will share it. Abhinav sir.
Sure. One more time, ma'am, you can try by sharing your screen, not the sharing the PPT. So I think it will work for you. Just you can try one more time by sharing the screen. Yeah.
Let's see.
Now,
Yeah, ma'am.
yeah.
Yeah, it's visible.
Again, it's gone. So
Yeah, I don't know what is happening because I am sharing screen.
okay.
Is it okay now?
Yes, ma'am.
No, then it is
No, no,
again going. I
Ma'am,
don't know something.
no.
ma'am, I'll tell you the steps. Ma'am, just follow them. When you open the sharing tray,
Uh-huh.
then there's a option browse.
Windows, I'm getting two options. There's a browse OneDrive, browse my computer. Okay.
Yes, ma'am.
Huh?
Then you
Yes.
can go for upload from my computer,
Yes, I'm selecting. Huh?
and then you can select the file which you want to.
Yeah, I have selected.
Okay, ma'am. Click OK. That's done.
Yeah. Can you see?
No, ma'am.
Ma'am, we will just email you and share the slide from here only.
Yeah, but it's in my screen now. I don't know. Yeah.
Ma'am, your screen is not visible actually.
Ma'am, you can mail it to me. You can write my ID,
Yeah. Tell me.
ANKIT.
Yeah, Ankit, we have received the ma'am slides.
You have received?
Ma'am, we have received your slides.
Okay. Yeah. Good. Okay. So are you going to open that?
Yes, ma'am. Please wait for 2 minutes.
Otherwise, now my screen is visible or no? Still it
Yes,
is.
ma'am. Actually, it is visible now. You can try in full screen mode if you want.
And oh yeah, I don't know whether full screen will work. Otherwise, this mode is also fine. This is 80%. I think I can go ahead with this.
Yes, ma'am. If you want, you can.
Okay. Yeah. Okay. So sorry for the delay. So a very good morning to all of you. So in today's session, I will be talking about unsupervised classification techniques. So yeah, so unsupervised classification. Yeah, again something has happened.
Ma'am, I have shared the screen.
Oh,
Is
okay,
a
you shared.
yes, ma'am.
Yeah, okay, fine. I can see.
Ma'am,
Ma'am,
you
you
can
can
click
actually
on take
click on.
control.
Ma'am, there is an option as take control.
Yeah.
You can take the control now. Yes, ma'am.
Okay, sure. Yes. So yeah, sorry for the delay. So yeah, I will be discussing on unsupervised classification techniques. So unsupervised classification is a, it's a kind of it's a machine learning approach only. So machine learning is nowadays very popular, and there are different paradigms of machine learning. One is called the supervised classification, and the second one is called the unsupervised classification. Then we can have the semi-supervised classification. So basically unsupervised classification is one important paradigm of machine learning. And in today's lecture, I will give you a brief overview of some recently developed techniques for unsupervised classification. So this is my web page address www.iitp.ac.in/Riparna. So you can visit my web page, and you can there are many. I am working in this particular field of unsupervised classification for I think more than 12 years now. So there are many publications related to this particular topic, and we also applied this particular topic in solving several real life problems of natural language processing or bioinformatics or text mining. So maybe you must visit my web page to see the applications of unsupervised classification. So this is the in today's session, there are three key concepts that I will be discussing on. One is the clustering. So you can see from the figure that clustering means grouping of objects. So you have a set of objects or set of samples, and you want to somehow make a group of this set of samples. So you don't know the class levels. Unlike supervised classification, you don't have any access to the class levels. So basically you would like to apply some similarity measure, or basically in the similarity measure, and based on the similarity measures you would like to group the points into different clusters. So points which are somehow similar to each other, they should be put into one cluster, and so basically that way we need to maintain some grouping. So basically this is called the clustering. So clustering means in an unsupervised way we want to make a group of points. So points would be grouped according to their internal similarity. So points which are very much similar to each other, they will be grouped into one category or one cluster, and the other points would be in some other clusters. So now in the process of forming the clusters, some similarity measures are required. So similarity measures are basically used to define the similarity or dissimilarity between two points. Okay, so how basically by using the similarity measures we can determine the distance of the similarity between 2 points. In the literature there are many existing similarity measures, so I will briefly discuss about them. I will name few of those similarity measures, and few of the similarity measures we will be also using in our proposed approaches. Then there is a third key concept which is called the multi-objective optimization. So you are, from the name itself you can understand that here we have to simultaneously optimize multiple conflicting objective functions. So for example, suppose if you want to purchase a car, so there maybe one objective could be cost or the price. So you want to somehow minimize the cost or the price. But there is also another objective which is the comfort. So you want to basically maximize comfort and you want to minimize the cost. So these two are somehow conflicting objective functions, and you need to simultaneously optimize them. So it is not possible to minimize cost while maximizing the comfort. So this is an example of conflicting objective functions, and that's why basically we need to apply the concept of multi-objective optimization for solving these real life problems where you are having multiple conflicting objective functions.
Excuse me, ma'am. Sorry to interrupt, ma'am. Ma'am, you can just see that in the top you might be having an option of take control.
Take control, yes.
Ma'am, you can click that. Yes, ma'am. Now you can change the slides according to yours. Yes, ma'am.
Yeah.
Thank you, ma'am. Thank you.
Yes. So basically this is the slide on clustering. As I mentioned that clustering is the unsupervised classification. So classification means you have to categorize the objects into different classes. Like you have a tumor, and maybe you can categorize the tumor into benign or the malignant. So these are the two possible categories. So for example, in a banking sector, you can easily find out the high risk customer and the low risk customer. So low risk customers are customers who could be given some loans or who could be given some credit cards. And the high risk customers are those customers, they are having low salary, their age is also, like, you know, there is a category of customers who are at high risk, and maybe you will not afford to provide some loan to these customers, or you will not afford to provide some credit cards to these customers. So these are examples of the classification task. So classification tasks are very common in real life. In almost all real life scenarios, there is a classification task. Like you are, as I mentioned, now this because of the corona, so you know, even the CT scan images, can we categorize the whether the person is having COVID-19 or he or she is suffering from simple pneumonia. So this is also a kind of a classification task. So given the CT scan or given the X-ray images, can we categorize whether the patient is suffering from COVID-19 or he or she is suffering some simple pneumonia. So this is basically, these are some examples of the classification task. And you know, for solving the classification task, one popular approach is unsupervised classification, or the cluster, or the supervised classification. So here basically somehow you have to give some supervision. So supervision means some samples with the class labels must be present. Okay, so you have to give the system that, see, these are the CT scan images of some COVID-19 patients, and these are the CT scan images of some pneumonia patients. And now from those images, the model will try to learn the pattern based on which it can differentiate between these two classes. So that is basically the classification task, the supervised classification task, where some label data is presented, and based on the label data, the system can generate some patterns or the rules based on which the classification can be done. But in case of clustering, such label data is not given. So clustering is basically simply grouping of objects into different category, into different classes based on their similarities or the dissimilarities. So like you can see here in this figure, so here basically you can see that no label data is given, but based on the similarity, we can categorize the objects into two different categories of the classes. So classification in general, it denotes supervised classification, where we have some label data present, and based on the label information, we can categorize the objects in different classes. But in case of unsupervised classification, no such labeled information is present. Based on the similarity or the dissimilarity, we need to group the objects into different classes. So this is the more or less the categorization of the clustering algorithms. You know, clustering is a very old field of research, and there are many works available in the clustering domain. So like there are some hierarchical methods available. So hierarchical methods assume that all points belong to a single cluster. So initially you can assume that there is only a single cluster, and then you keep on dividing the single cluster into some subclusters. So this is called the divisive. You understand that initially there is only one single cluster, and then you have to keep on dividing this single cluster into some small clusters, and this is called the divisive clustering algorithm. Then you have the agglomerative clustering algorithm, where you have where the concept is just the opposite of divisive. Here we assume that if we have n number of points, then there are initially n number of clusters. So each point belongs to a cluster, and then we need to somehow merge some close by clusters to generate a big cluster. So this is called the agglomerative. So it's just the opposite of divisive. Here, so in agglomerative, we start with n number of clusters, where n is the number of samples present in a data set, and then we can somehow combine two clusters into a big cluster. So this is the agglomerative clustering. Now there is this partitioning approach. So partitioning approach means the data set is divided into k number of clusters. So it's not a hierarchical approach that in a hierarchical way we'll be generating the clusters. But here if suppose you want k number of clusters, the data set will be divided into k number of clusters. So k means, k midwide, these are some examples of the partitioning approaches. Then there is also a algorithm called the DB scan. So DB scan is basically a density based approach. So density means points which are somehow very much close enough to each other. They basically they which are in a high dense region, they should form one cluster, and clusters are separated by low dense region. So this is the primary motto of DB scan, that we need to find out the highly dense clusters separated by low dense region. And k-means and k-midwives are partitioning approaches. So here the cluster is divided into k number of groups, and then basically based on the similarity or the dissimilarity, k number of clusters can be formed. So in k-means basically we aim to minimize the compactness. So compactness is nothing but the distance from center to all the points in a cluster. So center is basically the average of all the points. So you have to calculate the distance from center to all other points in the cluster, and this compactness has to be minimized. So then we have some graph based algorithm as well. So we can assume that points basically define a graph like structure, and then we can apply some graph partitioning algorithm to generate the clusters. Or we can also have some model based clustering algorithms like expectation maximization and the self-organizing map. So expectation maximization is basically assumes that clusters are following the Gaussian distributions. So according to expectation maximization, we assume that clustering is nothing but a mixture of Gaussians. So you only have to estimate the mean and the variance of a particular Gaussian. So that is called the expectation maximization. So we have to somehow estimate the parameters of the Gaussian distribution. And in self-organizing map, this is an unsupervised neural network based approach. So it basically maps a high dimensional space into a two-dimensional space. It is feature selection as well as clustering. First is it maps a high dimensional space into a two-dimensional space, and then in the two-dimensional space it produces the clustering. This is called the self-organizing map. So these are the various approaches of clustering, and these are the most popularly used clustering algorithms. So now let us discuss about the concept of optimization. So optimization, you understand that optimization means you have to optimize some objective function. Now the objective function could be one or it could be many. So for example, if you want to purchase a car, suppose only one objective, or you are optimizing only one objective function, that is the cost. Then this is an example of single objective optimization. But if you are optimizing multiple conflicting objective functions like cost and comfort, and you know it is not possible to simultaneously optimize these two. You want to minimize cost and you want to maximize comfort, and that is not possible simultaneously in real life, because if you want to increase comfort, then the cost will also go high, and if you want to minimize cost, comfort will be compromised. So these two are basically examples of conflicting objective functions, and this is an example of multi-objective optimization. So multi-objective optimization basically deals with simultaneous optimization of multiple conflicting objective functions. So more than two or more than that number of objective functions. And that way it basically produces a set of solutions on the final Pareto optimal set, and this set is called the Pareto optimal solution. So you can see that here there are three solutions on the surface, 1, 2 and 3. So if you compare solution 1 with respect to solution 2, so solution 1 is having a high value of safety, but solution 2 is having low value of bridge weight. So we can't say that solution 1 dominates solution 2 or solution 2 dominates solution 1. So these two solutions are called non-dominating to each other. So basically this is our Parrot optimal surface, where there are multiple conflicting objective multiple non-dominated solutions. So basically these solutions are called non-dominated to each other, because solution 1 is better with respect to one objective, but solution 2 is better with respect to another objective. So we can't say solution 1 dominates solution 2 or solution 2 dominates solution 1. So these are examples of non-dominated solutions. And now after basically any multi-objective optimization algorithm produces a set of non-dominated solutions on the Pareto optimal surface, and then the user has to select one solution from this final Pareto optimal surface. Depending on the user's need, the user can select any of the solutions. So this is the formal definition of multi-objective optimization. So you have to find the vector of decision variables which will satisfy the M inequality constants and P equality constants, and simultaneously optimize the M number of objective functions. So there are some constants, inequality and equality, and simultaneously it will optimize the some objective functions. So there is no concept of global optima, and it produces a set of trade-off solutions which is called the Pareto optimal set. So here you can see that suppose there are two objective functions f4 and f2, and both are of maximization type. So now if you compare solution 1 and solution 2, solution 1 is better with respect to f2, but solution 2 is better with respect to f1. So we can't say the solution 1 dominates solution 2 or solution 2 dominates solution 1. So these two solutions are non-dominated solutions. And the set of all the non-dominated solutions is called Pareto optimal surface. But if you compare solution 5 and solution 2, so for both the objectives, solution 5 is basically dominated by solution 2. So basically for both the objectives, you can see the solution 2 is having higher objective functional values than solution 5. So solution 5 is dominated by solution 2. So there are many existing multi-objective optimization algorithms in the literature. Mostly evolutionary algorithms. You know, evolutionary algorithms are some popular search and optimization tools. They basically mimic our natural evolution process. So they provide near optimal solutions for complex, hard and multimodal problems. So there are many existing evolutionary algorithms like genetic algorithms, differential evolution, etc. And these algorithms are very popular in solving single objective optimization problem. But here these algorithms are extended for solving the multi-objective optimization problem. So a multi-objective optimization algorithm must guide the search towards the global Pareto optimal front, maintain solution diversity in the Pareto optimal front. So basically these evolutionary algorithms are extended for solving the multi-objective optimization problem, and basically they used to guide the search towards the global Pareto optimal front, and they used to maintain solution diversity in the Pareto optimal front. So there are many existing multi-objective optimization algorithms. So some are evolutionary based, some are nature inspired, some are physical property inspired. So evolutionary algorithms are basically this Vega, MOGA, NSGA, NSGA2. These are some popularly used evolutionary algorithm based multi-objective optimization technique. Then there are some nature-inspired multi-objective optimization technique like particle sum optimization, the multi-objective optimization version of particle sum optimization, or the multi-objective version of the ant colony optimization. So these are some nature-inspired algorithms, multi-objective PSO and the multi-objective ant colony optimization. Then there are some physical property-inspired algorithms like MOSA and AMOSA. These are some physical property-inspired multi-objective optimization algorithms. So now we will basically discuss how multi-objective optimization can be used to solve the clustering problem. So in recent years, researchers are working on developing some multi-objective optimization based clustering algorithms. Okay, so basically, you know, these are two different paradigms, multi-objective optimization and the clustering. So in this particular talk, I will discuss how multi-objective optimization can be used to solve the clustering problem. So why multi-objective optimization in clustering? Because in clustering there are multiple conflicting objective functions. Like while you are partitioning a set of points, at that time you want to somehow minimize the intra-cluster distance. So intra-cluster distance is the within cluster distance. So in a cluster there are many points and you want to somehow minimize the similarities between a set of points which are in a particular cluster. So this is called the intra-cluster distance. And the inter-cluster distance is basically the separation between two clusters, and this has to be maximized. Okay, so separation between two clusters has to be maximized and the intra-cluster distance has to be minimized. So these two are basically two different objective functions, and we have to basically optimize these two objective functions simultaneously. We have to minimize the intra-cluster distance, we have to maximize the inter-cluster distance. So what are the key factor determining the efficiency of a clustering technique? So basically one factor is basically the proximity or the similarity. So proximity is a distance measure which determines the similarity. So basically proximity or the similarity basically calculates the distance between 2 points. So basically you can see that suppose there are many points and we can calculate the similarity between 2 points by using some distance measure. So while we are performing the clustering, distance measure plays a very important role, because if the points are somehow similar, if the distances between the points are somehow less, then only we are going to put those points into a single cluster. So basically the distance of the similarity measure play a very important role in clustering. I can see some hands, somebody is raising some hands. So when to take the question at the end, or there will be some chat as well?
We will take at the end, ma'am.
Okay, okay. Achha, some people are raising their hands. That's why I just mentioned. Okay, so basically distance measure plays a very important role, and there are many existing distance measures. You know, the Euclidean distance is a very popular distance measure, popularly used in many domains. Whenever you need to calculate the distance between two real vectors, then Euclidean distance plays a very major role. Then city block distance is also another important similarity distance measure. I will discuss about the some symmetry based distance measures. So these symmetry based distance measures are developed in recent years. So they used to determine whether a particular point is symmetric about a particular line or about a particular center. So you know, symmetricity is very common in our real life. There are many symmetrical objects around us, like human face is an example of symmetric, human body, then leaves of plants. There are many symmetrical objects around us, and there must be a way of measuring the amount of symmetricity of a particular sample with respect to a particular point or with respect to a particular line. So motivated by this, some symmetry based distance measures are developed in recent years. So these are called the point symmetry based distance and the line symmetry based distance. Then in order to measure, you know, for in the text, like if you are working with the text data, then first the text data has to be converted into a numeric vector. So there are different ways of converting the text data into numeric vectors. Either we can use the TF-IDF based representation, or we can use the, you know, we can use some semantic representations, like we can use the What2Vec. What2Vec is a recently developed deep learning based tool which basically converts a word into its vector representation. So and then after getting the vector representation, if you want to measure the similarity between two words, then the quotient similarity can be used. Symmetric conditional probability is one way of computing the similarity between two words. Point-wise mutual information is also a way of measuring similarity between two words. Then there are also some gene ontology based similarity measures. So how to determine goodness of a clustering technique? So cluster validity measures are very popular now, basically nowadays. So this cluster quality measures basically somehow they used to measure the quality of a particular partitioning. So as you can, we will soon see that given data set, there are different ways of partitioning a data set. It's not a unique way of partitioning the data set, but you know, depending on the objective function, we can somehow partition the data set into multiple different ways. So there are different cluster validity measures existing, external indices and the internal indices. So external indices, they basically use some actual class labels. They basically compare the obtained partitioning with the actual class labels. So like, you know, adjusted RAND index, classification accuracy, F measure, Minkowski score, J-card index. So these are some external cluster validity indices. They are basically somehow trying to match the similarity between the obtained partitioning and the actual partitioning. So you already have the information of actual partitioning, and now we can simply compare the obtained partitioning by an algorithm with the actual partitioning. So this is called the external. So why external? Because it utilizes some external information. And for the internal, no class label is required. So they are basically somehow relying on the internal measures. So here no class label is required. So we can have many internal measures like Zibeni index, PBM index, FCM index, Silute index, DB index, DAR index, mean square residue, row variance. So these are some internal cluster validity indices, and they basically somehow compute the similarity. They basically somehow quantify the quality of the partitioning based on compactness and the separation. So basically in any clustering paradigm, we want to minimize the compactness and we want to maximize the separation. These are the two motivations of clustering, and these indices are basically factors of compactness and the separation. So now why multi-objective clustering techniques? So there are several motivations of formulating the clustering problem as a multi-objective optimization problem. So first of all, given a data set, it is not possible to uniquely partition the data. There are different ways of partitioning the data. Number two is that if you are only optimizing a single quality measure while you are partitioning the data, then maybe you will not be able to capture all types of clusters, because a particular quality measure is biased towards a particular structure. So if your partitioning is having a variety of clusters, then and if you are optimizing only a single quality measure, then it is not possible to identify all structures from a partitioning. So this motivated by this, we are basically formulating the clustering problem as a multi-objective optimization problem, and we are simultaneously optimizing different quality measures, and as a result we are determining different types of clusters from a data set. For example, see this example here. Suppose this is a data set, and now we can either have 3 clusters or we can have 2 clusters. So both possibilities are there. Either you can basically join these 2 overlapping clusters into a single cluster, or we can have you can treat them as 2 different clusters. So either we can have 3 clusters or we can have 2 clusters. So this is an example. This is also an example that given the data set, there are different ways of partitioning the data set. So either we can have the correct solution, we can have the locally connected solution, or we can have the compressed solution. So there are different ways of partitioning the data set. So multi-objective clustering decomposes the data set into similar groups, maximizing multiple objectives in parallel. So multiple objectives can be simultaneously optimized, and then basically that way you will be able to determine different structures from a particular data set. So here we have the spiral structures, we have the hyperspherical structures. So if you optimize multiple quality measures simultaneously, then we will be able to extract different structures from the data set. So basically, now I will present a particular clustering algorithm which is developed in recent years. So which is a multi-objective optimization based clustering algorithm. So which basically tries to overcome the limitations of the existing algorithms. So k-means is basically a very popular clustering algorithm. K-means tries to partition the data into k clusters so that the compactness is basically minimized. So k-means requires the clusters to be hyperspherical and of almost equal size. K-means known to get stuck at local optima. Hierarchical methods like single linkage clustering techniques require the clusters to be non-overlapping. Algorithms like expectation maximization methods make assumptions about the data distribution. Heuristic techniques like genetic algorithms, simulated learning, etc. often optimize measures that cannot capture clusters of any shape, size, or convexity. So we aim to develop a general purpose clustering technique which avoids getting stuck at local optima, which can detect clusters that need not necessarily be convex, may have overlaps, and can be of any size and density. Even the number of clusters determined automatically. So basically, this is the aim, that we want to develop a multi-objective optimization based clustering technique which can avoid getting stuck at local optima, can detect clusters having different structures, and also is capable of determining number of clusters automatically. So this is a decision problem in clustering. How many clusters you want to generate, that is a decision problem, and most of the existing clustering techniques assume that the number of clusters is already known, like k-means, k-medoids, hierarchical clustering algorithms. They basically assume that the number of clusters is already given by the users. But in real life it is very difficult to assume this value, because you will not be able to visualize the data set, and that's why you will not be able to understand how many clusters are there. So basically we developed a new multi-objective optimization based clustering technique which uses AMOSA as the underlying optimization method. It can determine the appropriate k and the appropriate partitioning simultaneously. So basically, that AMOSA is the underlying optimization technique, and it is automatically determining the appropriate value of number of clusters and the appropriate partitioning, and basically it can work with any data sets of any kind. So basically, data sets of having different types of clusters are basically clustered by using this method. So now, any multi-objective optimization technique or any, as I mentioned, that evolutionary algorithms are very popular in solving the multi-objective optimization problem. So now in evolutionary algorithm, the main concept is the concept of a chromosome of a solution. So somehow we have to represent the clustering problem in the form of a solution or a chromosome or a string. So string basically there are different ways of representing a particular clustering solution. So either we can have the center based encoding or we can have the point based encoding. So in center based encoding, the cluster centers are used to encode the partitioning. So suppose there are two clusters and they have the cluster centers C1 and C2. So in the chromosome we can represent only the cluster centers. So now the chromosome is consisting of two centers. Or there is another way of representing the partitioning, that is called the point based encoding. So suppose you have 22 number of points. So basically now the chromosome is of length 22 and the corresponding value indicates that this point belongs to cluster 1 or cluster 2. Like x1 is 1 means x1 belongs to cluster 1. x22 2 means x22 belongs to cluster 2. So this way, these are the two possible ways of representing the clusters. So but each is having its own limitations or the drawback. So like if you are following the center based representation, then the length would be limited, because if you have k number of clusters, then the length of the chromosome would be k. length would be limited, but here by this method we will not be able to determine the structures which are not of hyperspherical shaped. So by center based embedding we can only determine the clusters which are hyperspherical in shape. In point based encoding, the length is very high, because if you have 1 lakh of point, then the length of a chromosome or length of a string would be 1 lakh. So that is the limitation of the point based encoding. So now what will happen if you have a structure like this? So this is not a hyperspherical shape clusters. If you are following the center based encoding, then it is not able to identify this kind of structures. And point based encoding, as I mentioned, these are very lengthy. So how to deal with these connected structures? So no symmetricity exists. Center based encoding fails to capture symmetry property, can be decomposed into several small hypersymmetrical shape clusters. So basically this way what we are doing, we are dividing the big cluster or the long cluster into some subclusters. So these subclusters are somehow symmetrical in shape or symmetrical in structure. You can see that this long cluster is divided into some subclusters, and these subclusters are somehow symmetrical in nature. So now we can somehow represent this clustering structure by using the subcluster centers. So the first cluster is divided into 8 subclusters, and the second is divided into 10 small subclusters. And the centers of these 8 subclusters and the 10 subclusters are used to represent the chromosome. So Ki is the number of clusters, Cik is the number of centers for kth cluster of ith string. Suppose D is the dimension, then the length of the string is basically summation of all the subcluster centers into D, because each subcluster is of D length. So in each cluster is having some subclusters. So the length of the string is summation of all the subclusters into D. So now the number of clusters is chosen randomly. So Ki is assumed to lie in between Kmin to Kmax, and the number of subclusters per cluster is also lying in the range of Cmin to Cmax. So the number of clusters we are defining in a range, and the number of subclusters per cluster is also lying in a range. Now for the in any evolutionary algorithm, we used to maintain a population. So population is basically consisting of multiple chromosomes. So population is basically consisting of multiple chromosomes, and chromosomes are somehow initialized randomly. So chromosomes are nothing but the set of cluster centers, and this basically initialization is done randomly. So partly random, partly based on 2 different single objective algorithms in order to obtain a good initial spread of solutions. So 1/3 of the solutions of the archive initialized after running single linkage for different values of number of clusters. Another 1/3 is initialized after running k-means, and the last 1/3 initialized randomly. So initialization procedure is basically partly random, partly based on 2 different single objective algorithms. So 1/3 of the solutions are initialized by running single linkage for different values of number of clusters. 1/3 is initialized after running k-means, and 1/3 is initialized randomly. So this is our chromosome structure. So you know that for each chromosome or for each solution, we are randomly selecting a value between k-min to k-max. So Ki is the number of clusters, and the value of Ki is randomly chosen between k-min to k-max. K-min is the minimum possible number of clusters, and the k-max is the maximum possible number of clusters. Now suppose we have selected Ki equal to 3. That means there are 3 clusters. Now each cluster is having some subcluster centers. So the number of subcluster centers is also selected in a range. So Cmin and Cmax are the minimum and the maximum possible subcluster centers. So for the first cluster, maybe we are having only 2 subcluster centers. For the second cluster, we are having 3 subcluster centers. For the third cluster, we are again having 2 subcluster centers. So these way solutions are generated. So solutions are diversified in nature. You can see they are having varying number of clusters, and they are also having varying number of subcluster centers per cluster. So these two are randomly decided. So the number of clusters will be randomly decided, and number of subcluster centers per cluster is also randomly decided. So that way the population is consisting of a diversified set of solutions. Now how to assign points to different clusters? So first we have to sum all the subcluster centers. Okay, we have to sum all the subcluster centers, and then a point is basically assigned to a subcluster center. So basically first we have to identify all the subcluster centers, and then a point is assigned to a cluster K where this is followed. So basically we have to find out the similarity distance between a particular point and a cluster, and then the point is assigned to the minimum distance cluster. So basically the point X is assigned to the particular subcluster center which is at minimum distance. So here you can see, suppose there is a particular point and we want to determine the distance from this point to all the clusters, and then we have to assign this point to the minimum distance cluster. So assign to the cluster with respect to which its distance is the minimum. Now for the fitness computation, there are three objective functions. So first, for the fitness computation, first that all these subcluster centers are merged to generate the clusters. So all these subcluster centers are merged to generate the k number of clusters, and then on those merged clusters we are computing the fitness of the objective functions. So as this is a multi-objective optimization technique, so we are simultaneously optimized multiple objective functions. So I have already mentioned about the cluster validity indices. Cluster validity indices are the cluster quality measures, and they used to check the quality of the clusters. So basically there are three cluster validity indices which we try to optimize simultaneously. So one is the I index. It is a cluster validity index based on Euclidean distance. So it detects appropriate value of number of clusters and the appropriate partitioning from datasets having compact, well separated hyperspherical clusters. And second is the SIM index. So as I mentioned that symmetricity is one important factor. Yeah, as there are many objects around us which are examples of symmetricity, we can also assume that some type of symmetricity exists in the cluster structure. So basically we would like to get some symmetrical shaped clusters from the data set. So because of that, we are optimizing some symmetry based cluster validity index. So this symmetry based cluster validity index is based on the symmetry based distance. It detects appropriate k and the proper partitioning from datasets having symmetrical shaped clusters irrespective of their geometrical shape, size and convexity. And then there is a third cluster validity index which is the connectivity based index. It basically tries to determine the connected structures, the structures which are not hyperspherical shaped, which are not symmetrical in shaped, but if the structures are somehow connected, then this connectivity based index is trying to determine the connected structures from a data set. So what is the, so first let us discuss about this point symmetry based distance. So as I mentioned, this point symmetry based distance is developed to quantify the amount of symmetricity of a particular point with respect to a particular cluster center. So whether the point is symmetric with respect to the cluster center or not. So DPSXC is a new point symmetry based distance between X and the cluster center C. So in order to measure this, we have to first find out the mirror image of X with respect to C. So you know, if X is a particular point, C is the cluster center, we need to find out the symmetrical point of X with respect to C, or the mirror image of X with respect to C. Suppose that is X star. Now we have to search for nearest neighbors of X star. So suppose the nearest neighbors of X star are D1 and D2. So then the point symmetry based distance between X and C is equal to the average of D1 and D2 into Euclidean distance between X and C. So basically we are determining k nearest neighbors of the mirror image point, and then we are taking the average of this k nearest neighbors and then multiplying that with the Euclidean distance between X and C. So this way, by using this distance, we are able to detect different types of structures, like all the symmetrical shape clusters can be easily determined by using this kind of distance. By using the point symmetry based distance, we will be able to determine different types of symmetrical shape clusters. So cluster validity measure. So now based on this symmetrical distance, a cluster validity index is basically developed. So this cluster validity index basically quantifies the partitioning in a symmetric way. So if the clusters are symmetrical in nature, then this validity index value would be high. But if the clusters are not symmetrical, then this symmetric cluster validity index value would be low. So this is a newly developed point symmetry based cluster validity index. So suppose there is a partition of the dataset X and there are k number of clusters. So then the symmetric this SIM index is basically it is having three factors. Capital K is the number of clusters, 1 by EK. EK is the symmetrical compactness. So you can see it is the symmetrical compactness of all the points with respect to the cluster center. And then the third is basically the separation between two clusters. So in the Euclidean space, so whether two clusters are well separated or not. So SIM index is basically a combination of three factors, 1 by K into 1 by EK into DK. So EK is the symmetrical compactness. It measures the symmetrical distance between the cluster center and all the points in the cluster. This is a symmetrical compactness. DK is the separation between two clusters and capital K is the number of clusters. So the objective is to maximize this index in order to maintain the actual number of clusters. Three factors complementary in nature, so they are expected to compete and balance each other critically for determining the proper partitioning. So these three factors are complementary in nature, so they are expected to compete and balance each other critically for determining the proper partitioning. So basically here there are two factors. EK denotes the total symmetrical deviation of all clusters and DK denotes the maximum separation between any two cluster centers. So this way basically the goodness of the partitioning is measured. So EK denotes the symmetrical deviation of all clusters and the DK denotes maximum separation between any two cluster centers. Index. So basically I index is a Euclidean distance based cluster validity index. It is again it is very much similar to the SIM index only, but in SIM index while we are computing the compactness, there we have used the symmetry based distance. But in I index, in order to compute the compactness, the Euclidean distance is basically used. So EK is basically a summation of all the Euclidean distances. So basically you can see that there are some cluster centers and there are some points. So we are simply calculating the distance between the cluster center and the points. So that is basically the Euclidean distance. So we are computing the compactness in terms of Euclidean distance. Then we have the separation, which is the distance between two cluster centers. That is the separation. Now there is this connectivity based index. So connectivity based index, as I mentioned earlier, connectivity based index basically tries to determine the connectedness of the clusters. So it is based on the concept of relative neighborhood graph. Suppose X be a set of points represented as X. There are 2 points Xi and Xj are said to be relative neighbors. If the following condition holds, the distance between X and Xj is basically less than equal to maximum distance between xi xa or xj xk. So basically it is the thing that suppose if these are the 2 points xi and xj, and there is no other point in this particular region, in the overlapping region, suppose there is no other point, then these 2 points are called the relative neighbors. So suppose xi and xj are 2 points and there is no other point in this particular region, then xi and xj are called the relative neighbors. So basically we have to generate the relative neighborhood graph as follows. So we have to find out the region of influence. So the region of influence is this region. So if the region of influence does not contain any point, then xi and xj are connected by an edge. And the edge weight is equal to the equivalent distance between xi and xj. So if the region of influence is empty, then we want to add an edge connecting xi and xj, and the edge weight would be equal to equivalent distance between xi and xj. Now after forming the relative neighborhood graph, we have to generate the connectivity based index. So relative neighborhood graph is basically first constructed, and now we have to find out the all possible path between the midpoint of a particular cluster and the each point in the cluster along the array and along the relative neighborhood graph. So midpoint, we have to find out the all possible paths between the midpoint and any point in the particular cluster. So suppose there are total p number of paths. Number of edges along the ith path is n edge I, and then all these edges will have some length. So now we have to find out the maximum jump along a particular path, and if there will be p number of paths, we have to find out the minimum of the maximum jump. So basically we have to first find out the maximum jump along a particular path, and then we have to find out the minimum of those maximum jumps. Shortest distance equal to the maximum jump along the path, not the sum of the distances along the path. So this is the thing that you can see that this is the given a midpoint. Suppose this is the midpoint and this is a particular point. There are different possible paths between the midpoint and the particular point. We have to find out all possible paths. Then we have to find out the maximum jump along a particular path. So for example, here the maximum jump is this. And then we have to find out the minimum of those maximum jumps. So connectivity-based index is defined like this, that in the numerator we have the shortest distance between the midpoint and all the points. So midpoint and all the points, this is the shortest distance, and the denominator we have the minimum separation into n. So minimum separation is basically the distance between two midpoints. So ni is the total number of points present in the ith cluster. Mi is the midpoint of the ith cluster, n is the total number of data points. Objective is to minimize the connectivity based index. So basically we want to minimize this shortest distance. That means the points should be connected to each other. If the points are very much connected, then the numerator would be minimized and the denominator would be maximized if the centers are far apart. Means there is a big separation between the midpoints. So that way you basically have to minimize the connectivity based index. So basically, and these three objective functions, Sim index, I index and the connectivity based index. So these three objective functions are simultaneously optimized by the search capability of any multi-objective optimization technique. So the proposed framework is very generic. The objective functions can be optimized by using any optimization technique. It could be NSGA2, it could be AMOSA. So there are many existing multi-object optimization algorithms available in the literature. So any of those optimization techniques can be utilized for simultaneously optimizing these three objective functions. So now suppose we have a solution, and suppose now we want to basically somehow want to change the solutions. So I already discussed about the solution representation. So you know that we are determining the number of clusters randomly or automatically, and then for each cluster we are also determining the number of subclusters randomly or automatically. And those subclusters are basically used to used for the chromosome or the solution representation. So now once we have the solution representation, we can change the solution. So there are different ways of changing the solution. One is the modifying a cluster center. We can modify each subcluster by a small amount, or we can insert a new subcluster center, or we can delete a new subcluster center. So these are the three ways of modifying the subclusters. So either we can modify each subcluster by a small amount, or we can insert a new subcluster center, or we can delete a subcluster center. Or the second is that we can also increase the number of clusters by 1, or we can decrease the number of whole clusters by 1. Which is the thing that suppose this is our original string. Now either, as I mentioned, that either the first option is changing the subcluster centers. So initially these are the two subcluster centers. Now we are changing the subcluster center. Second is that we can insert some new subcluster center. So initially there were two subcluster centers. Now we are inserting one more subcluster center. And third is we can delete subcluster centers. So initially there were 3 subcluster centers. We can make it 2. Here also there are 3 subcluster centers. We have make it 2. Now in the perturbation type 2, we are simply increasing the number of clusters by 1. So initially there are 3 clusters. Now we have inserted one more cluster, and now we are having 4 subclusters, 4 clusters. Similarly in perturbation 3, we are simply deleting one whole cluster. So basically we have taken the results. Basically we have used a AMOSA, which is a one of the recently developed multi-objective optimization based technique, and as the underlying optimization strategy, and the results are compared with other different clustering algorithms. And as the evaluation metric, we have used the Minkowski score. So Minkowski score is an external cluster validity index. It basically checks the similarity between the obtained partitioning and the actual partitioning. So we already know the actual partitioning. We have to determine the similarity between the obtained partitioning and the actual partitioning. The solution with minimum Minkowski score is selected as the best solution. These are the different results. You can see that our algorithm is not only capable of determining the number of clusters, but is also capable of determining the subcluster centers for each cluster. So like here you can see there are 2 clusters, and our algorithm is capable of determining 2 clusters. Here also there are 2 spiral clusters, and our algorithm is capable of determining two subcluster centers. You can see that our algorithm is capable of determining different types of clusters having different shapes and sizes or the convexities, and it is also capable of determining the number of clusters automatically. So we have compared the proposed approach with several existing approaches, and you can see the results. So you can see that our approach attains the minimum Minkowski score, and it also attains the actual number of clusters. So here you can see that our algorithm is almost able to capable of attaining the actual number of clusters and also subcluster centers per cluster. Now this algorithm is applied on a real life problem, which is called the search result clustering, which is a very important problem of information retrieval. So search result clustering means, suppose you are searching in the Google or any web browser regarding a particular query. So suppose you are searching with the word Puma. Puma could be an animal name, or Puma could be also a brand name. So if you only search with the term Puma, then your basically search engine will retrieve a set of web snippets. So now can we categorize these web snippets into different categories based on the semantic similarity? Like some web snippets which are talking about Puma as a brand name should be clustered into one group, and the web snippets which are talking about Puma as an animal name should be in another group. So this is called the search result clustering. So what says induction? What says induction means that some words are having several senses. Like the word bass, I can hear bass. Here bass means the low frequency tone. But if you are saying that they like grilled bass, then here bass is a type of fish. So this is called the word sense induction. So certain words are ambiguous in nature. The meaning of those words depend on the context, so in which it is appearing. So a task of automatically inducing the different senses of a given word is called the word sense induction. So this is the search result clustering, that puma, word puma can have several meanings. So puma can refer to basically puma can be a brand name, or puma can be a animal name. So if you are searching with the word puma, then basically we can categorize the web snippets into different categories. So organizing results returned by a search engine in response to a query or keyword. So we are giving the query to the search engine. Search engine is retrieving the results, and now we are basically categorizing the results into different classes or different clusters based on their semantic similarity. So this is the overall search result clustering algorithm, and there are many existing algorithms, but all of these algorithms are single objective optimization based. So there are some basically optimizing a single quality measure for determining the clustering. So basically we aim to develop some multi-objective clustering based solution framework for the search result clustering. So here, there are two objective functions that we have simultaneously optimized. One is the cluster compactness. As I mentioned, cluster compactness is basically within cluster similarity. So in a cluster there are many points and there is a center. So we need to determine the similarity of all the points with respect to the cluster center. So this is called the intra-cluster distance similarity. So this intra-cluster similarity or the cluster compactness has to be minimized. And then there is this inter-cluster similarity or the cluster separation. So this means the distance between two cluster centers should be maximized. So this is the steps of the proposed algorithm. We have to create the word vectors. We have to create the global vocabulary. We have to create the similarity matrix. We want to initialize the population of archive element. We have to compute the membership and the update cluster center. Compute objective functions for each solution. Form parallel front. Apply mutation. So there is a loop, and this loop continues for n number of times. So basically for each solution, we are computing the membership values, we are updating the cluster centers, we are computing the objective functions, then we are applying the mutation. So this is a loop, and this loop is continued for n number of times. And finally, we are selecting the final solution using the FB cube method. So in order to represent the solution, we are basically extracting the important words from each snippet. So a web snippet is a collection of words, and this is the representation of a web snippet. So a document is a collection of words and the corresponding frequencies. So suppose D1 is having 3 words, W1, W2, W3, and these are their frequencies. So basically a web snippet is a collection of words, and each web snippet is each word is having its own frequency. So based on the TF-IDF method, we are selecting the important words, because there will be many stop words also. We are simply removing the stop words. We are simply maintaining the basically the significant topical words. So this is our global vocabulary. Global vocabulary is nothing but the set of all the words which are unique to different documents. Then we compute the similarity matrix. So similarity is the word-to-word similarity. By using this formula, symmetric conditional probability, joint probability of two words by the individual probability of individual words. So by using this symmetrical conditional probability, we are computing the similarity between two different words. Now for the string encoding, we are basically following this structure. So number of clusters of a particular solution varies over a range. So like you know that now suppose this is a solution. So the number of centers in a particular solution varies over a range. So it varies over 2 to root n. And we assume that each center is basically composing of some words. Here we have assumed that each center is having two words. We also varied this value so that how many words should be should represent a particular center. So here each center is represented by two words. Then you can see this is our population initialization. So there are multiple members in the population, multiple chromosomes are in the population, and each chromosome is of variable length. So the number of clusters is varied over a range. We generate a random number between 2 to root n, and those many number of centers are used to represent a particular chromosome. So basically, this way basically we are initializing the chromosomes. Now then we are computing the membership value. So for a particular web snippet, we need to assign this web snippet to any of the cluster centers. So for example, here there are 4 cluster centers. So these are C1, C2, C3 and C4, and in the column we have all the documents. So now the value could be 1 or 0. If the document is assigned to a particular cluster, then the value would be 1. If the document is not assigned to a particular cluster, then the value would be 0. So this is the membership matrix. So we are computing the symmetrical conditional probability for computing this for basically assigning this for generating the membership matrix. So AS is the denotes the similarity measurement between the point DJ and cluster centroid MK. Okay, and this way by using this formula we are computing the similarity between a document and a midroid. So by using this formula. And then in the mutation operations, so there are 3 types of mutation operation. Either we are inserting a new cluster center, or we are deleting a new cluster center, or we are simply changing the existing cluster centers. So this way you are exploring the search space. So these are the 3 types of mutation operations, and by using these 3 types of mutations, we are exploring the search space. So these are the datasets used, ODP 239 and the MORISQ. So ODP 239 is having 239 number of queries, and the number of web snippets are 25,000. And in MORISQ we are having 11,000 number of web snippets. For evaluation metric, we have used the FB cube. This is a weighted average of precision and recall. These are some results. So so basically then what we did, I just would like to introduce this concept that nowadays people are working on multi-view clustering techniques. So what is multi-view learning? A particular sample or a particular data can be represented by multiple views. Like a person can be represented by the face, by his face, or by a person can be detected by using the face detection algorithms, or the iris detection algorithms, or by using the fingerprint. So these are called the different modalities of the different views. A certain type of information or the representation format in which information is stored. So basically, you know, obtained from multiple sources or different feature spaces. So basically, we can have certain type of information or the representation format in which information is stored. And can we utilize all this information simultaneously while we are performing this clustering? So this is the multi-view data. So multi-view, there are several examples of multi-view data in real life. Like you can see the video. Video is a collection of audio signals and also the images. So video is also a multimodal data. Like suppose you are a web page. A web page can be represented by the images content in the web page or the text portion content in the web page. So a web page can have two different views. A multilingual document can also have multiple views depending on the language used. So basically, this is the thing that we did a thorough literature survey, and this is our motivation that existing multi-view based clustering techniques are again single objective optimization based. So they do not optimize multiple quality measures simultaneously to identify the partitioning. So in our work, we have simultaneously optimized multiple objective functions simultaneously to develop a multi-objective, multi-view based approach. So here three paradigms are combined in one frame: multi-objective optimization, clustering, and the multiple views of data. So two objective functions are the inter-cluster distance and the inter-cluster distance. So we are minimizing the inter-cluster distance, we are maximizing the inter-cluster distance. So the compactness is minimized and the separation is maximized. And we are also maximizing the agreement between partitionings, often using different views. So all these objective functions are simultaneously optimized, and as a result, we are getting a multi-objective optimization based multi-view clustering technique. So basically, you can see that each dataset is having n samples, each described by d number of features, and there are a smaller number of views. There are some objective functions, and we have simultaneously optimized these objective functions to get a consensus partitioning. So what we are doing, we are now for each view we are generating a partitioning, and then we are checking the similarity amongst the partitionings obtained using different views. Okay, so basically now this is one additional objective. So we are having in the chromosome or in the string representation, we are having the features from different views, because now a sample is represented by different views. So we are able to extract features from each view, and all those features are represented in a particular chromosome or a particular solution. And then for each view we are getting a particular partitioning, and somehow we are checking the similarity amongst the partitionings obtained using different views. And that similarity is checked with respect to agreement index. So basically, these are the objective functions. So basically, individually, we want to improve the partitioning with respect to a single view, but side by side, we also want to improve the agreement amongst the partitionings obtained using different views. This is our flowchart that we state representation and the archive initialization. We apply k-means on the individual view and obtain different partitionings. Then we check the similarity amongst different views. We compute the PBM index or the I index value for the individual partitioning, and we also compute the agreement index to check the similarity between different partitionings. So all these objective functions are simultaneously optimized by using the search capability of MOSA or any other multi-objective optimization technique. And then we apply genetic mutation operator to generate new solutions. Think that now in the chromosome we are having attributes from different views. So attributes of view 1 for cluster center 1, attributes of view 2 for cluster center 1. So this way we are having feature values from different views. Now formation of clusters. So clusters are generated by using this way. So each center, basically there are many centers, and each document is given to a particular, is assigned to a particular center. Three types of mutation operations: either we are changing the existing cluster center by some value, or we are simply deleting a particular cluster center, or we are inserting a cluster center. So there are three types of mutation operations. As the objective functions, we have used this PBM index or the Zybeny index. PBM index is very similar to the I index only, and Zybeny index is also basically a combination of compactness and separation. Numerator, we are having this compactness, distance between a point and the cluster centers, and the denominator is having the separation. And then, as I mentioned, the agreement index is basically checking the similarity between two partitionings. So suppose there are two partitionings. So we are computing the similarity between two partitionings, and then we are optimizing these objective functions simultaneously. Now for the consensus partition generation, suppose this is the opt-in partitioning by view 1, this is the opt-in partitioning by view 2, has to determine the overlaps. So for example, the B is very much overlapping with E, A is very much overlapping with D, C is very much overlapping with P. So first we are determining the mapping, and then we are getting the overlapping region, and then we are selecting a cluster center from that overlapping region. So this is the consensus partitioning. So we have shown the results on the different data sets. So we are using the two different views, the original set of attributes, and the second is we have applied the principal component analysis of the PCA to generate the second view. Okay, because you have to somehow generate the two views. The first view is the original set of attributes, and the second view is obtained after applying the principal component analysis. So these are some results. So you can see that yes, we are able to outperform the existing techniques. Then just to conclude that the search result clustering problem can also be formulated under multi-view learning. So here in the search result clustering, there could be different views like syntactic view and the semantic view. The web snippets can be represented by syntactic view and also the semantic view. So syntactic view is measured by using the TF-IDF, term frequency, inverse document frequency schema, and the semantic view is measured by using the symmetrical conditional probability. So we have shown that if we are considering these two views and we are solving the search result clustering problem in a multi-view setting, then that is more better compared to the single view setting. Then we have also introduced the image view, because the web pages are combinations of text and the images both. So can we maybe two web pages are very much similar with respect to the images, but dissimilar with respect to the text. So basically we are using two different views, image view and the textual view. For the image view, pretend 19 layer VGGNet is used to extract high level features. And for the textual view, we are combining the benefits of both word-to-vec and TF-IDF. So these are the two views, image-based view and the textual view that we have used. And then we are optimizing the multiple objective functions simultaneously, and we are generating the clusters. And we have shown that basically these are the three data sets that we have used, MBN, ModSQ and the ODP. And results obtained are indicative that if we are considering multiple views, then we are getting much improved results. So yes, so basically this is the thing that in my talk I have presented some multi-objective optimization based clustering techniques, and I have also shown how multi-objective optimization can be extended for handling the multi-view data. So multi-view data means data sets are represented using multiple views, and we need to somehow incorporate these multiple views while we are clustering on the partitioning the data. And in future we would apply this multi-view concept for scientific documents. We would like to apply the multi-view concept for the cyberbully detection and several other cases. So yes, so now I am almost done. So maybe now I can take some questions.
If somebody has any question, they may raise their hands. Yes, Akash, you can unmute yourself and ask your question.
Hello, am I audible?
Yeah, you are
Yes,
audible, Akash.
First of all, thanks, ma'am, for a wonderful session. I think we got familiar with a lot of new terms. However, in the interest of time, I will just ask two questions. First being, what is the basic difference between PCA and SOM, self-organizing maps? And the second is, when you're deciding the value of K for K means, is elbow method better than AMOSA, or is it vice versa?
Okay, so your first question is what is the difference between PCA and the self-organizing map?
Right.
Okay, yeah. So PCA, it's a kind of a statistical measure. So basically, it calculates the variance covariance matrix and then the eigenvalue, eigenvectors, and then it tries to project the data in such a direction where there is more variance. So that is the underlying principle of principal component analysis, that it tries to project the original data in such a direction where there is more variance. Okay, so it is a kind of a statistical technique. By you have to calculate the variance covariance matrix, then the eigenvectors you have to determine, then you have to sort those eigenvectors based on the eigenvalues, and then select the top k number of eigenvectors and project the data along those eigenvectors. This is the principal component analysis. And in self-organizing map, it's a kind of a neural structure. Okay, it's a neural network based structure where there is an input layer and there is an output layer, and it somehow maps the input layer into output layer, and the output layer is basically a two-dimensional grid. Okay, so that the input, suppose in the original in the original space, some inputs are nearby, some inputs are very similar to each other. Then in the output space also, they will be mapped to the same neuron. So basically, both of these are two feature selection techniques, but they are basically they are relying on different principles. Okay, so PCA is relying on a statistical principle, and the self-organizing map is basically using this neural structure to transform the higher dimensional feature space into lower dimensional. So it is basically taking a weighted average of higher dimensional feature space to map to a lower dimensional space. So that is the difference between self-organizing map and the PCA. And self-organizing map, there is one advantage, that it not only performs the feature selection, but it also clusters the data. So you will be also having a clustering of the data in the lower dimensional space. So that is another advantage of self-organizing map. But in case of PCA, after applying PCA, you again have to use some clustering algorithm to obtain the partitioning. And coming to your second question, whether the elbow method is better or the AMOSA. So elbow is a kind of a manual method. You need to vary the k. You have to run k-means. Then you have to plot, like you have to check the value of some cluster validity index. Either you can take the silhouette index or any other cluster validity index. You have to plot a, you have to somehow plot a diagram, and you have to see for which value of k it is attaining the best value. So elbow is a kind of a, it is a manual task, but in AMOSA it is done automatically. So the algorithm is basically automatically determining the value of k. You only have to run AMOSA only once, and it will basically provide you the value of k and the optimal number of partitioning. Akash, is it clear to you?
Yes, ma'am. Thanks for clearing. Thank you.
Vandana, next question, please.
Due to shortage of time, we will take one more question, please.
Yeah. Thank you, ma'am. First of all, for the thank you very much for our informative lecture. I wish to ask one question regarding that. That generally we in the multi-objective optimization, when we perform for the clustering, if we have a 3 objective, at the after final iteration we get a Pareto front. That is almost all solutions are like a good one, right? So in that case, in the clustering, which how do we select a particular solution? Because after that we have to go for a single. If it is a semi-supervised type of classification, that first we will perform a clustering, and after that classification, then we have to select a one cluster among the Pareto friend. And the second question, and ma'am, the second question is that in one work, when you are creating a like a multi-view, that first one is with the original features, right? And the second features we are doing with the PCA. So
Yes.
generally PCA is using for like a reduction. So in that I have a doubt ki the original feature space size will reduce in a PCA, right? And when we are finding the clustering, the whether we have to do individually on in the both spaces.
Okay, so let me tell you the answer your first question. So the first question is how to select a single solution from the parallel front. So yes, again there are many different methods available. Okay, it's again a research problem. This is a research problem, and many researchers are working in this along this line. So in our case, what we have done, we have used some other cluster validity index. Like we have used the SIM index, I index, and the connectivity-based index as the objective functions. So what we did, we used the silute index, which is another cluster validity index. We calculated the values of silute index for all the optimal front, and then we selected the solution which is having the highest value of silute index. Or there could be other method, like if you draw the curve, this parallel surface, you will see there is a niche region. So this
Yeah.
niche, the solution corresponding to the niche region can also be selected. When there is a sharp change in the objective functional values, that solution can also be chosen as the base solution from the parallel front. So yes, so these are the two ways that we have used. Okay, so in
Yeah.
our study, and the second point that you have mentioned in the multi-view, we use the original features as one view, and we have applied PCA and then use that view as the second, those set of features as the second view. So what we did, we retained the same number of features. We only projected the data in a different space. So like that we initially we have a original space, and then we projected the data in the other space, so where the variance is more. Okay, that was the purpose. We have not
Okay.
reduced the features by PCA, but we
Okay.
just
Only
projected the data.
only for the projection purpose
Yeah,
we
yeah,
have
yeah,
used,
yeah,
right?
yeah. Yes. Because with these data sets, the two views were not possible. Like when I am using the search clustering, then it is quite easy because you have the image information, you have the text information. You can easily have two different views. Or
Yeah.
but in the UCI machine learning repository data, you have only single features available. So that's why we have also used the PCA to generate the other view.
Okay. Thank you, ma'am.
Pooja Bharadwaj.
Hello.
Hi Pooja. Yeah, hello.
Yeah, ma'am. Good morning, ma'am.
Good morning.
Thank you for the wonderful lecture. And I want to know about how intercluster distance and intracluster distance will work to solve the multi-objective function. Sorry, MOO,
Yes.
multi-objective optimization.
Okay.
Yeah.
So it's a intra-cluster distance means the distance within the similarity within a cluster. So you have
Yeah.
to find out the center, which is the average of all the points, and then you calculate the distance from the center to all the points in the cluster. Okay. So this is the intra-cluster distance, and the inter-cluster means cluster to center distance. So if you
Yeah.
have k number of clusters, then the center to center distance is the separation or the inter-cluster distance. So now you can simultaneously optimize. So basically you have to read the paper on AMOSA or the paper on NSGA2, because I did not go into the details of NSGA2 or the AMOSA, but these algorithms are developed for solving the multi-object optimization problems. So these algorithms are capable of optimizing multiple conflicting objective functions. So this intra-cluster and the inter-cluster distances are used as two objective functions, and then this AMOSA or the NSGA2 can be used to optimize them.
Okay, ma'am.
Yeah,
Okay,
so
ma'am.
you please read the paper on AMOSA or the NSGA2. These are very popular papers. Okay, you can see the citations are very high. So those are easily downloadable. If you don't get, you write to me. I can send you the PDFs. You please
Yeah, ma'am.
read those papers, and then you will see how they are handling the multiple objectives.
Okay, ma'am.
So there is some changes in the basically NSJ2 is based on genetic algorithm. So they are modifying some steps of genetic algorithm so that it can accommodate the multiple objectives.
Thank you, ma'am. Thank you so much.
क्या अमूल हाथ भावेश
Hi.
Vishaka,
Hi,
please
Kamul.
propose vote of thanks.
Okay, sir. Thank you, Dr. Saha, for taking some time out of your busy schedule and delivering this informative session on unsupervised classification techniques. Your lecture was attended by nearly 700 participants across the country, and I'm pretty sure they must have benefited a lot from it. Personally, I found your lecture to be quite insightful, and ma'am, believe me when I say that you are quite an inspiration for the women working in the field of science and technology. Now, I would like to invite Professor Singh to thank Dr. Saha and present her with the virtual memento.
Thank you, madam, for
Thanks a lot,
accepting
sir.
accepting our invitation and giving us time for our short-term course. And in future also, we'll be taking your help to conduct this short-term course, because I think our participants have really enjoyed your lecture and learned a lot from your lecture. So
Thanks a lot for giving me this opportunity, sir. Thanks a lot for the invitation. Yes, thanks a lot. I'm honored to get this invitation.
Yeah. It's honor for us also, madam, to have you in our short-term course. So I would request you to in future also, if we are conducting our short-term courses, so I'll be taking your help.
Sure, sir. I'm always ready. I'm
okay.
Yeah.
Thank you very much, madam. Thank you.
Thank you, sir. Thank you, sir. I am leaving then. Bye.
Yeah, bye. Bye.